Hello everyone, welcome to this presentation entitled Investigation of the Use of Switch Capacitor Converters as LED Drivers. This presentation corresponds to the paper of the same title presented at the IES annual meeting in 2023. The authors of this paper are myself, J. Marcos Alonso from the University of Oviedo, Spain, Guirgis Saki Abdelmessi from the University of Burgos in Spain, Marco Antonio Dalla Costa from the Federal University of Santa Maria in Brazil, Yueshi Wang and Jijie Wang from Harbin Institute of Technology in China. This is the outline of this presentation. First, we will see an introduction. Then we will present the analysis of the voltage Doubler switch capacitor converter. We will talk about PWM dimming applied to switch capacitor-based LED drivers. We will show some laboratory tests, and finally we will present the conclusions of this work. This slide shows the three common solutions to implement LED drivers. We have the linear current source, in which we use a transistor here in order to limit and regulate the current through the LED. So it operates in closed loop by measuring the current and acting on the transistor, so the current through the LED is going to be constant. So this solution is good because it can provide current regulation. It's simple because it has also a low number of components. The cost is reduced. There is no switching, so there is no EMI generation. And the main problem is that the efficiency is going to be low because of the linear operation of the transistor. Another disadvantage is that we cannot obtain at the output a voltage which is greater than the input voltage. So these type of solutions can only be used in step-down applications. The second solution is the use of switch capacitor converters. In these converters, we employ only switches and capacitors in order to implement the converter and to regulate the current through the LED. This is a solution that is better than linear current source for higher powers, for low, medium power applications, because we can get a better efficiency. Also, we can obtain at the output a voltage that can be higher or lower than the input voltage, so this is another advantage. Also, these type of converters don't employ inductors, so they can be very small and flat, and even they can be easily integrated even in silicon. Also, because they don't use inductors, the EMI generated by this type of converters is low. And finally, the third solution is the use of switching mode power supplies. So in this case, we use switches and diodes, inductors, capacitors in order to supply the current through the LED. So we need more components. These type of converters are then more expensive. Therefore, they are usually employed in higher power applications in which we can assume the higher cost. Also, they operate in closed loop, regulating the current through the LED, and they can provide a very good efficiency. They are also flexible because we can have even several parameters to control the converter, but they are going to generate also higher electromagnetic interference because we need to employ inductors. In other cases, we need coupled inductors or transformers, so we are going to have higher electromagnetic radiation and therefore higher interferences. So the goal of this paper is to investigate a little bit further the use of switch capacitor converters in LED driver applications. In this work, we have chosen the voltage Doubler SCC in order to do this investigation. The main reason is that with this converter we can obtain at the output a voltage that is nearly double the input voltage. So we have this very interesting feature of the SCC. but the main conclusions of this work can be extrapolated to other converters. So in this slide we are showing the basic analysis of this converter. We have here the schematics of the voltage doubler SCC. We have two switches here and two diodes. We have the switch capacitor at this point, and then we have the output capacitor to filter the output, and then we have the LED load. Here below we have the signals to do the driving of the switching. Phi 1 is for switch S1 and Phi 2 is for switch S2. So as we can see, we are activating switch 1 during a one given interval that has a duration equal to t on. Then we have a dead time, and then we activate the other switch, switch 2. Then we have another dead time, and so on. So in this part here we have the two intervals of operation. In interval phi 1 we have switch S1 closed, so we are charging capacitor C through diode D1 in this way. So capacitor C is going to be charged up to a voltage which is equal to Vi minus V gamma. V gamma is the forward voltage of diode D1. So this is the charge that is going to be stored in capacitor C during this interval. Then during interval phi 2 we close switch 2 and we open switch S1. And then what we are doing is to send current this way through capacitor C to the output capacitor and to the LED load. So in this case, as we can see, the voltage that we are going to have here at the end of this period is equal to VO minus VI plus V gamma, which is again the forward voltage of D2. We are considering that both diodes are with the same characteristics. So this is the charge that we are going to have at the end of the period phi 2 in capacitor C. Here below we can see the current circulating through the capacitor. During phi 1 interval we have a positive pulse of current charging the capacitor, and during the second interval phi 2 we have a negative pulse of current coming out of the capacitor. So now we can say that the DC current that we are going to have through the LED lamp is the difference in the charges, both charges QC1 and QC2, times the switching frequency. And then we get this expression. And finally, rearranging, we can say that the output voltage is this value here, twice the input voltage minus the diode's forward voltage minus R resistance, the equivalent resistance Re, times the DC current through the output. And the equivalent resistance has this value here, which is 1 over Fc. This is the common behavior in steady state of a switch capacitor converter. From the analysis before, we can obtain this equivalent circuit here with a voltage source, which is twice the input voltage minus the forward voltage of the diode. We have the equivalent series resistance, and then we have the output with the output capacitor and the LED load. And these are the equations that we have seen before. So we can see this graphically here. We are representing here the current through the LED as a function of the voltage across the output, across the LED lamp. So the behavior of the switch capacitor converter is as shown here. We have this linear equation, so we have this representation for the current versus the voltage. And for the LED lamp, of course, we have this other representation corresponding to the behavior of a diode or several diodes in series with a given threshold voltage and a given series resistance. So the slope, as we know, of this part of the characteristic is equal to 1 over the series resistance of the LED load. So from the intersection of these two characteristics, we can obtain the operating point that we are going to have for the LED lamp. So we can get the output voltage and the output current. And we can also see that using the series equivalent resistance, we can modify the slope of this characteristic of this line, and therefore we can modify also the operating point. So in principle, the variation of Re can be a possibility to regulate and to control the current through the LED. We can modify this resistance by using the switching frequency so that we can change the current through the lamp. Here we have the equation corresponding at the end to the current that we are going to have through the LED, and even we can calculate the efficiency that we are going to have. The problem of modifying Re is that if we increase Re, then we are going to have higher losses in the operation because we are going to have losses here, and therefore the efficiency is going to decrease. Also, in the paper we have analyzed the operation and we can obtain the current ripple that we are going to have through the LED lamp. So it's the voltage ripple divided by the series resistance of the LED lamp, and it can be calculated using this expression. In this work, we have also revisited the switching operation of these converters because it is unavoidable to have some series resistance and series inductance when charging and discharging the switch capacitor. So in this case, if we analyze this equivalent circuit that we are going to have during the charging and discharging process, we can obtain this differential equation. And because of the small value usually that we have for the series inductance, we can assure that we are going to have an exponential response as shown here. These are the roots of the characteristic polynomial in which this time constant tau L and tau C can be calculated, and finally this is the response of the current that we are going to have during this interval. So this is the current that we are going to have during the charging and discharging processes. Here in this part of the slide we can see the current waveforms that we are going to have for different values of the tau L time constant, which depends basically on the inductance, and for a given value of the tau C constant, which depends on the value of the capacitor. So we can see how for small values of tau L, so small values of series inductance, we have a waveform which is similar to the ideal waveform, but when we increase a little bit the series inductance, then we are going to have this type of waveform which is softer. And in principle this is good because we are going to have a current that starts from zero and has a lower peak in the current. So this will reduce the switching losses and also the EMI generation. Here we have the expressions corresponding to the time instant at which the peak of the current is going to appear, and this is the value of the peak current that we are going to have for each waveform. In this work, we have also investigated the use of PWM dimming with HCC converters. So, because the converter, the switch capacitor converter, is going to behave as a voltage source at the output, it seems advisable to use a switch in series with the lamp. So when we open the switch, then we have no current circulating through the lamp, and when we close the switch, then we have current through the lamp. In this work, we want to operate at quite high switching frequency, above 20 kHz, so we can avoid audible noise, And therefore, the equivalent circuits that we are going to have are as shown here. We have that during the on interval, the switch is closed, so we have this equivalent circuit. And when the switch is open in the off interval, we have this equivalent circuit. From these two circuits, we can obtain the DC average equivalent circuit, as shown here. For this average equivalent circuit, what we have to do is to average the value of the series resistance of the LED, and then we can obtain this value here, RD over D, where D is the PWM dimming duty cycle. And then from this equivalent circuit we can obtain the average current that is going to circulate through the lamp, the peak value of the current, and also the average voltage that we are going to have across the lamp. Here we have the waveforms. This is the PWM signal. This is the DC voltage across the lamp. We can assume that because the PWM switching frequency is going to be high, the output voltage remains almost constant, and this is the waveform corresponding to the current. We have current during the on interval and zero current during the off interval, and the average current is I0 that we can obtain using this expression here. What we can see also is that the peak current depends on the duty cycle. So if the duty cycle decreases, we are going to have a higher value of the peak current. To verify this behavior, we have done a simulation. Here we have our switch capacitor converter. This is the load. We have here the switch for the PWM dimming in series, and this is the integrated circuit to control the switch capacitor converter. We are operating at 100 kHz switching frequency for the converter and at 25 kHz for the dimming frequency. So now here below we can see the output voltage for different values of the dimming duty cycle for 0.1, 0.2, 0.5 and 0.8. So we can see that the voltage remains almost constant at each duty cycle with a very small ripple. And below we can see the current circulating through the lamp. So we can check that for a high value of the duty cycle, 0.8, we have this waveform in light blue. So the peak value is 1.2 amperes. But when we decrease the duty cycle, the peak value is increasing. So for example here, for a duty cycle of 0.1, we get almost 2.4 amperes peak. So in principle, this is not a good behavior, because if the peak value is changing, the chromaticity coordinates of the light emitted by the lamp are going to change also. So it could be advisable to implement some kind of strategy in order to keep the peak value change as small as possible. Fortunately, there is a thermal effect that can help us to have a not so high change in the peak current, because if we analyze here this equation which we have obtained before, the peak current is given by this expression here. So if we decrease the duty cycle in order to decrease the power in the lamp, then the temperature is going to decrease. And in a LED, we have that the threshold voltage is going to increase. So if the threshold voltage increases here, then the peak current tends to decrease. So due to the effect of the temperature, as we are going to see in the experimental results, the change in the peak current is not so high as expected. So here we have the laboratory prototype. This is the schematic. These are the different values that we have used. The lamp is 44 volts, 1 ampere. We have used a series switch here to implement the dimming and a series resistance to measure the current through the lamp. This goes to a microcontroller that generates both the signal, the switching signal for the converter, and also the switching signal for the dimming. Here are the different values of the elements that we have used. And this is a picture of the prototype. This is the microcontroller. This is the display showing the switching frequency and the dimming level. And here we have the switches, the dimming switch, and the output capacitor, the switch capacitors. They have been implemented using ceramic capacitors. This is the driver for the half bridge here of the converter. And finally, we have here the LED lamp. These are the characteristics of the lamp. The lamp is a Cree X lamp CMA 3090. So these are characteristics obtained from the datasheet of the manufacturer. So this is the voltage versus the current through the lamp for different values of the temperature. And we have obtained the model of the lamp at the different temperatures. So we have these values, in which we can see that the series resistance remains almost constant, but the threshold voltage is increasing when the temperature decreases. And these are the basic waveforms of the converter. Here we have the switch capacitor current during the charging and the discharging process, so we can see that the waveforms are as we have presented in the theoretical analysis. Here we have 5 amperes per division, so this is something like 10 amperes peak. And here we have the current and voltage of button switch N1, so is the current and voltage in this switch here. So again, we can see the voltage and then the current through the switch, which corresponds to the charging process of the switch capacitor C here. And here we have the experimental results corresponding to the LED lamp current at different dimming ratios. So here is for continuous operation. And then when we reduce the dimming duty cycle, then we have these different waveforms in which we can see that the turn on and turn off times are extremely low. So the dimming operation is very good. We can reach dimming duty cycle of 0.1 with very small value of the average current and very quick on and off transitions. Regarding the peak value, we can see that here is around 1.2 amperes and the peak value is increasing, but we are not reaching so high values as in the case of the simulation, and this is due to the thermal effect that we have explained before. So the maximum value in the peak current is 1.7 amperes. So this is good for the dimming operation of switch capacitor converters. And finally, here we have some more experimental results. This is the lamp current in amperes as a function of the dimming ratio. So we can see that the change in the current is quite linear when we modify the dimming ratio. This is the lamp power also as a function of the dimming ratio, which is also very linear. And finally, we have the efficiency here as a percentage. So as we can see, when we operate at maximum dimming ratio equal to 1, the efficiency is 90%, and then when we decrease the dimming ratio, we get smaller values of the efficiency, because here the power is very small and we have losses in the series switch. So this is the reason why we have low efficiency at low power. So finally, as conclusions of this work, we can say that we have done an investigation on the use of switch capacitor converters in LED driving applications. We have presented the most relevant characteristics of the studied switch capacitor converter, which is the voltage doubler. We have studied in detail the application of the PWM dimming to the voltage doubler converter, and we have obtained the equivalent circuit of the converter under dimming operation. It has been observed that the use of series PWM dimming performs very well in switch capacitor converter LED drivers, allowing the converter to achieve a highly accurate dimming control. Relevant thermal effects on PWM dimming operation have been identified, which in this case are favorable for the use of PWM dimming because they allow to decrease the peak current circulating through the lamp. The efficiency obtained was considerably high, more than 90% at rated output power. And finally, we have also seen that the efficiency decreases when reducing the output power by using PWM dimming, but in general, the efficiency keeps in a reasonable range, and this aspect has to be also investigated in future research to try to increase the efficiency at low dimming levels. Well, this concludes this presentation. I hope that you find this information useful. Please let me know through the comment section if you have any question. Thank you very much for watching, and I hope to see you in the next video. Goodbye now.